Hello, my phenomenal viewers, and welcome on today's episode. On today's episode, we are going to be answering this question on thermodynamics, and the question reads 8.0 kilograms of hot liquid A initially at 90 degrees Celsius are mixed with 3.0 kilograms of water initially at 22 degrees Celsius in an insulated container. If the specific heat capacity of liquid A is half that of water, determine the equilibrium temperature reached by these two liquids. So as we can see, the question is under thermodynamics. But before I provide a solution to this question, I would recommend that you should go grab a book and a pen and join me as I provide a solution to this question. So, solution. Now coming back to the question says 8.0 kilograms of hot liquid A initially at 90 degrees Celsius. So we've been given the mass of liquid A, which is what? 8 kilograms. So let me use MA to represent the mass of liquid A. So MA, which is mass of liquid A, is equal to 8 kilograms. Then the initial temperature of liquid A is 90 degrees Celsius. So Ci representing the initial temperature of liquid A is 90 degrees Celsius. Now the mass of water has been given to us to be what? 3 kilograms. So MW representing mass of water is 3 kilograms. Then small Ci, which is the initial temperature of water, is 22 degrees Celsius. Then the question further says that if the specific heat capacity of liquid A is half that of water, so it shows that specific heat capacity of water in this case is equal to 2 times the specific heat capacity of liquid A, which means that if I divide both sides by 2, I'll have the specific heat capacity of liquid A to be specific capacity of water divided by 2. So this is the data that we've extracted from the question. Now, how do we determine the equilibrium temperature reached by these two liquids? So when these two liquids are mixed, heat is going to flow from the liquid that is at a higher temperature to the liquid that is at a lower temperature. So since it is liquid A that is at a higher temperature, it is going to flow from liquid A into water, which is at a lower temperature of 22 degrees Celsius. And we are going to use this condition, which is the heat that liquid A is going to lose will be the same heat that water is going to what? Gain, since the container is what? Insulated. So heat lost by liquid A is equal to heat gained by water. So remember that the heat either supplied or gained by any substance is usually calculated using this formula. Q is equal to mc delta theta. So the heat given out or gained by a substance is usually equal to the mass of that substance times its specific heat capacity times its change in temperature. So the question, remember, is asking us to determine the final temperature, which is what? C. We don't know this final temperature, the temperature at equilibrium state. So at this equilibrium state, there is no net heat flow, and we need to determine the temperature when there is no net heat flow. So the heat that liquid A is going to lose, Q A, is equal to mass of A times specific capacity of A times a change in temperature. Now, remember that it is liquid A that is supplying the heat. So its change in temperature in this case would be its initial temperature minus its final temperature, since it is giving out heat. So it will be 90 degrees Celsius minus the temperature at equilibrium position. See, this temperature when the two liquids are at thermal equilibrium. So this is the heat that liquid A is going to give out. Now, the heat that water is going to receive, pure W, will be equal to the mass of water times the specific heat capacity of water times the change in its temperature. Remember that it is water that is gaining the heat. So it shows that the final temperature of water will be greater than the initial temperature of water, and the final temperature of water is the temperature at equilibrium state, which is T minus 22, which is its initial temperature. So at equilibrium, Cure A at equilibrium, Cure A is equal to Cure W. When equilibrium is reached, that is when there is no net heat flow. So this implies MACA into 90 minus T should be equal to MW CW into T minus 22. Permit me to demarcate the board. Now, what is the mass of liquid A? The mass of liquid A is 8. Now, what is the specific capacity of liquid A? It has not been given to us, so let me just maintain it. Let me say it is what? Ca times 90 minus T is equal to, what is the mass of water? 3 times, what is the specific capacity of water? It is Cw, but Cw has a relationship with Ca, which is Cw is equal to what? 2Ca. So instead of me writing Cw here, I'm going to write 2Ca. So remember, the specific capacity of water is 2 times the specific capacity of liquid A. So I want to write this specific capacity of water in terms of specific capacity of liquid A so that they can cancel at the end, times the change in temperature of water, which is T minus 22. So notice that Ca goes off with Ca. So I will be left with 8 times 90, that gives me 720 minus 8 times T, this gives me negative 80, to be equal to, this is now 6. 6 times T gives me 60 minus 6 times 22, this gives me 132. Now, if 132 comes this way and negative 80 goes that way, I will have 80 plus 60, which is what? 14T, to be equal to 720 plus 132, that gives me 852. So this shows that 14T is equal to 852. For me to have T, I simply divide both sides by 14. So it shows that the equilibrium temperature, or the temperature reached when equilibrium is reached between the two liquids, would be 60.9 degrees Celsius. So this is the temperature at equilibrium state, 60.9 degrees Celsius. So this is how you solve this question. And if you liked this video, please help me and share so that I can get to many students as possible. And if this is your first time coming across any of my videos, please do not hesitate to either follow me or subscribe so that whenever I upload videos like this one, you will be notified. And thank you for watching. Stay blessed.